All right, so the intermediate value theorem is probably something you have talked about in the past, perhaps in AIM 3 or in pre-cal last year, whichever one you happened to take last year. It's a pretty straightforward theorem. It has some very basic initial conditions that have to be met. The only initial condition really is that the function has to be continuous on some interval, some closed interval from A to B. So as long as we have a function that's continuous on a closed interval from A to B, the intermediate value theorem says that if you take any y value between f of A and f of B, so suppose we chose W, some number between f of A and f of B, well, there is some value C that is between A and B that when I plug it in to my function, f of C gives me W. And I can pick any value on the open interval between A or f of A and f of B. And no matter what value I choose, there will be a value between A and B that gives me that y value. That's what the intermediate value theorem says. Basically what it's saying is if I pick up my pen and try to draw from A to B and f of A to f of B, no matter how I do it, doesn't matter what it looks like in between, I will hit every single y value between f of A and f of B, no matter what. Okay? And they will all come between A and B. That doesn't mean that I might not get some of those values later on between f of A and f of B after B, or maybe even before. Right? I could get some of those values before or after, but I'm guaranteed that for every value between f of A and f of B, there will be a value between A and B that makes us get that y value. Does that make sense? Or no?
Yeah, that makes sense.
All right, cool. This is only true if the function is continuous on that closed interval from A to B. Okay. Hold on one second. I gotta deal with my kid's class. Give me just a minute. All right, sorry about that. I don't know. His teacher's having issues with Zoom, I guess. So sorry about that. We're gonna get to it here now. So the major consequence of the IVT, the intermediate value theorem, is that if the function goes from a negative value up to a positive value, that it must cross through the x-axis somewhere on that interval. That there must be at least one zero or one x-intercept or one root to this function between A and B. Okay. So if it goes from negative to positive. Does that make sense?
Yeah.
Okay, so we got the intermediate value theorem is telling us that basically any value between f of A and f of B we can get between A and B. Specifically, we can get an x-intercept if we need to, as long as there's a sign change on our continuous function from A to B. Cool, that's the basics of the intermediate value theorem. We're not gonna do a whole lot with it, except want to understand conceptually that's what it does. And we're gonna do one problem where we do what's called verifying the intermediate value theorem. And then we're going to do another one where we prove that there's a root, and then that's going to pretty much be all we do with it. Should be pretty straightforward. So we're going to start with verifying the intermediate value theorem on the closed interval 0 to 2. So for the function f of x equals negative x cubed. Any thoughts on how we'll start that? Any thoughts on how we'll start that? Or is the silence an indication that there are no thoughts on how we should start that? What should we start with? Any thoughts on what we should start with?
Checking if the function is continuous.
There we go. All right. Is f continuous on our interval 0 to 2? Is negative x cubed continuous from 0 to 2?
Yes.
Yes. Why? Because it is a polynomial. This is an acceptable reason for why a function is continuous on an interval, because polynomials are always continuous for all real numbers. So this function f is continuous on 0 to 2 because it's a polynomial. What's the next thing we should probably do?
Plug in 0 and 2.
Plug in 0 and 2. What's f of 0?
0.
And what's f of 2?
-8.
Perfect. So what the IVT says is that for every w I choose on the open interval from -8 to 0, there exists a c value on the interval 0 to 2. So f of c is equal to w. That's what the intermediate value theorem states. Okay, so how do we prove that that's true for this particular function? We are choosing a w on the interval -8 to 0, right? So how do I write that w is between -8 and 0?
It's just like an inequality.
Yep, that's exactly what it is. It should be w is less than 0, but greater than -8, right? That's telling us we're picking a w between -8 and 0. And we need to show that that gives me a c between 0 and 2. So effectively, I need to turn that w into a c somehow. Well, how can I turn that w into a c? What else do I know about the relationship between c and w?
Negative c cubed should equal w.
Perfect, right? F of c is equal to w. So negative c cubed is w. So now I can just replace that w with negative c cubed and solve this inequality for c. Divide by the negative, flip the signs when you divide by the negative, right? And then take a cube root, which gives us that c is less than 2, but greater than 0, which is exactly what we wanted to prove. For any w between -8 and 0, for this function, negative x cubed, w is negative c cubed, which shows us that c will come out between 0 and 2, or that we can get a c between 0 and 2. Everybody okay with that or no?
Yep.
Cool. I will ask you to do that once or twice on a homework assignment, but that's about it. It's not too bad. All right. Let's use the intermediate value theorem to do something even easier, to show that this function f of x has a 0 between 1 and 2. Any thoughts?
Would we set the function equal to 0?
Well, that we want to show that it does have a 0 between there, but setting it equal to 0, that's a tough equation to solve, wouldn't you say?
I guess so, yeah.
Yeah, I think that's a tough one to solve without graphing, and I don't want to have to graph it. I just want to know that there is one. I'm not concerned what it is. I just want to know that there is a root, or that there is a 0 between 1 and 2. So the intermediate value theorem would say that if f of x is continuous, right? And is f of x continuous?
Yes.
Yeah, it's continuous, and we're talking about on the interval from 1 to 2, right? Continuous on 1 to 2 because it's a polynomial. then if there's also a sign change between f of 1 and f of 2, then since it's continuous and 0 would occur between the sign change, then there must be a root or a 0 between 1 and 2. So we got to find f of 1 and f of 2. What's f of 1? F of 1 ought to be 1 plus 2 minus 6 plus 2 minus 3. So what is that? Negative 3, negative 4. Everybody agree with that? Good or no?
Yep.
All right. What about f of 2? Looks like f of 2 is 2 to the 5th. What's that? 32 plus another 2 times 2 to the 4th. So another 2 to the 5th. That's 64 minus, what is that? Minus 48 ought to be 16 plus 4 is 20 minus 3 is 17. So f of 2 is 17. So because 0 is less than 17 but greater than negative 4, there must be, by the IVT, a 0 on 1 to 2. So we know that there must be a place between 1 and 2 where the function has to equal 0 because it went from negative 4 to 17 and the function is continuous. Good or no?
Good.
Good.
All right. Those are the two basic things you'll need to do with the intermediate value theorem. That's all there is to it. All right. Next thing we're going to do is we're going to see if we can take this piecewise defined function and find a value or multiple values perhaps for a so that it's continuous for all real numbers. Okay. So whenever we're asked to show that something is continuous for all real numbers, the first thing we're going to want to look at is the two different pieces or three different pieces or 4 or 5 pieces that we might have. In this case, we just have 2 different pieces, right? We have a piece for when x isn't negative 1 and a piece for when x is negative 1. So for the piece when x isn't negative 1, is this rational function continuous for all other real numbers besides negative 1?
Yes.
Right, this little piece here has a discontinuity where at x equals negative 1, which is fine because x doesn't equal negative 1. But it's continuous everywhere else. And all rational functions are continuous. That doesn't say everyone. I don't know why I read everyone. Everywhere else, right? All rational functions are continuous for their domains. So a rational function is continuous on its domain. So if the function is, this function right here has a discontinuity at negative 1, that means that this function is continuous from negative infinity to negative 1, and it's continuous again from negative 1 to infinity because the only discontinuity is at negative 1. So that is generally an accepted fact that all rational functions are continuous except where they have these discontinuities. There's nothing else weird going on. Wherever their domain exists, they're continuous. Everybody okay so far?
Yeah.
So we've now shown that this function is continuous for everything except maybe at negative 1. And so all we have to do is show a value of a that makes it continuous at negative 1. And that means we're looking for continuity at a point, right? At x equals negative order to have continuity at a point, for a function to be continuous at a point, what do we need to have be true? 3 criteria that need to be met.
FC must be defined.
All right, there we go.
Little-
Stop there. That's the first one. F of C must be defined. So F of -1. What is F of -1? Where do I plug that in? Which part? Here or here? How do I find F of -1? Do I plug in -1 to ax plus 5, or do I plug it into the rational function?